Hi guys, in today's video we'll be discussing about an important topic for grade 9 and 11 and 10. What are scalars and vectors? We'll be focusing mainly on vectors, but we'll be having a good discussion on scalars too. So before we start with scalars and vectors, we're going to ask ourselves the question, what are physical quantities? Physical quantities. Okay. So the quantities which can be measured are called physical quantities. Pretty simple, right? Quantities which can be measured by physical means, or uh, let me make it quantities which can be measured with or by a instrument and accurately are known as physical quantities. So quantities which can be measured by an instrument and accurately. So physical quantities are of two types. What are they? First type are vector quantities and scalar quantities. Alright, so we're gonna start with scalar quantities. What are scalar quantities? Scalar quantities are the physical quantities which are expressed only by their magnitude. The magnitude is basically the unit and the numerical value of the quantity. So all scalar quantities need only their magnitude to represent them. For example, speed, a scalar quantity, it needs its unit, which is meter per second, and its numerical value, or together magnitude. So now I'm going to give some examples of scalar quantities. We have speed, we have distance, we have pressure. Okay, we have let's say work, we have power, we have mole, resistance, density. There are many. Resistance, density, etc. These are some examples of scalar quantities. So scalar quantities need only their magnitude to represent them. Magnitude is basically the unit and the numerical value. Numerical value. Now let's go to vector quantities. What are vector quantities? Alright. Vector quantities are the type of physical quantities that require their magnitude as well as their direction to represent them. So again, magnitude is just the unit and the numerical value, so number value, and direction is, we know our cardinal direction, north, south, east, west, so we don't have to specify that direction. A direction just means specifying which direction it's going to. We can do that using an arrow. So arrows are used a lot in vector quantities. It could be going in this direction, this and this, all different directions. So to represent a vector quantity, we need their magnitude, that is the unit and numerical value, and we need their direction. An example of vector quantity, say displacement. We usually represent displacement like this. This is called S bar. S stands for displacement, or its magnitude basically. S stands for, no, S is the unit displacement, and this stands for the direction. Alright, so another thing, when you, this is called a bar. This arrow on top is known as bar. So whenever we use this, the longer the arrow, the greater the magnitude of the vector quantity, and direction is specified. So the size of the arrow tells us the magnitude, and it obviously tells us the direction. Okay, now some examples of vector quantities are force, displacement, then there's velocity, and then there's momentum, there's impulse, weight, so many, etc. Okay, now, like I said, vector quantities are represented by their symbol and their direction and magnitude. So this will be known as, or said as, A bar, and A is the symbol for acceleration. Just putting that out there. Suppose we have F bar. This is force. We can have V bar, velocity. We can have P bar, momentum. Etc. Alright. So that's the introduction to vectors. Now two vectors are the same only and only if their magnitude and direction both and direction are the same. This is a very important statement, so you should pay attention here. So two vectors are the same only and only if their both magnitude and direction are the same. So usually we represent vectors using using arrows. Suppose we have a vector here, A bar, and another vector here, B bar. Alright, so A bar exerts a force. A bar is representing a force of 10 Newton, and so is B bar. So would both of these vectors be the same? Answer is no, because A bar is directed this way and B bar is directed this way. So even though their magnitude is the same, their direction is different. So a bar is not equal to b bar. Oh, a bar is not equal to b bar, but oh wait, I wrote a bar is not equal to b bar, but since their magnitudes are equal, we can represent the equal magnitudes in this way. So a bar, we have a bar here, and this represents the magnitude of a bar. So what this we can call modulus, or we can call it absolute value. These symbols are for that. So this represents the magnitude of a bar is equals to the magnitude of b bar. So whenever you see something like this or something like this, it means the magnitude of the vector. So this shows, even though the direction is not equal, the magnitude of a bar equal to the magnitude of b bar. This is how you represent magnitudes and direction. So suppose now we have two vectors. This is a bar and this is b bar. A bar is a force of 10 Newton and so is this. As you can see, they are in the same direction. So these two vectors are equal. Okay. So I'm just gonna revise once. Vectors are represented by the arrow with any letter here. So it could be v bar, which is velocity, a bar acceleration, p bar momentum, etc. Alright. Now let's talk about the angle between the vectors. Alright, suppose you have two vectors a bar and b bar. How would you represent the angle between these two vectors? So whenever you have a vector, this is known as the tail, which is the back part of the arrow. This is known as the head. So to represent an angle, you join the two tails of the vectors. So the good thing about vectors is that you can, keeping the direction and the magnitude same, you can place one vector and put it at some other position. So if you want to represent, if you want to put the tails of these two vectors together, you can put b in a sort of this position by keeping the direction and the magnitude the same. If you visualize it, you can tell that the figure will look something like this, the angle. Suppose this angle is theta. So you rearrange the vectors in such a way that their tails join. You can also rearrange them in such a way that their heads join. You can take vector A in this case, keep vector B the same. Take vector A in this case, put it in such a way that the head of vector A connects to vector B. So it would look something about like this. This is vector A bar. So this is also angle theta. So this angle, these both angles are equal. So when you join the tail and tail, you get an angle theta, and when you join the head and head, you also get an angle theta, which are equal to each other. So you can do either of the two. This is called tail to tail and head to head rearranging. So tail to tail and head to head rearranging. and that's how you find the angle between two vectors. So I have a question for you now. Let me just, okay, say you have the vectors a bar, b bar and c bar. Find the angle between a bar and say b bar, and also b bar and c bar, and the figure given to you is this. This is a figure. So a bar is like this, and this is 30 degrees. Oh, b bar is like this. This is b bar, and this is say 15 degrees, and c bar is like this, and this angle is say 45 degrees. So first we have to find the angle between a bar, one second, a bar and b bar. You can see a bar on this axis and you can see b bar. So we can connect both of their tails as they're on the same axis. So when you drag a bar, keeping this angle 30 degrees the same, you keep dragging it, and eventually you connect this tail, the tail of a bar to the tail of b bar. You will get 30 degrees on top plus 15 degrees on bottom. So the angle between a bar and b bar would be equal to 30 plus 15, because the total angle, because you would get 30 here, so this total angle will become 30 plus 15, which is equals to 45 degrees. And we have to connect b bar and c bar. How would you do this? This is an interesting one. So let me just, yeah, so the angle between b bar and c bar, so over here we can also connect the tails because they're on the same axis. So you imagine dragging b bar all the way till about let me just erase this c bar and write it over here. So imagine dragging b bar all the way till about here. So what would that mean? That would mean this angle of b bar would be the same, because you can't change the direction, right? So this, what I'm marking currently, it would also be 15 degrees, and the angle of total angle, I mean, is 45 degrees. So the angle between b bar and c bar would be equal to 45 degrees minus 15 degrees, which would be equal to 30 degrees. Let me just redraw this so that there's no confusion. Only b bar and c bar. This is b bar, angle 15 degrees, and this is c bar, angle 45 degrees. So imagine dragging b bar, the tail end of b bar, all the way. So you're dragging it. This angle would remain the same, because if the angle changes, that means the direction changed, and you can't do that. So you kept dragging this tail, keeping the 15 degree angle same across this, all the way till this tail reaches this point. So when that tail reaches this point, this line would be about like this, correct? And this angle is just 15 degrees, and this total angle is 45 degrees, as we can see. So what would be this angle? This angle would just, as I told before, be 45 minus 15, which equals to 30 degrees. And that's how you do this. All right. So now let's move on to multiplying vectors, and this will be our last topic. So let's say we're multiplying a vector by a real number. Or let's say you have vector a bar and you have the real number as, let's say, lambda. I hope you guys know what lambda is. It's a variable. So we have multiplying lambda a bar. Alright. So lambda, when you multiply lambda by a bar, which lambda being a real number and a bar being a vector, you get 4 cases. 1, 2, and 3, 4. What are these 4 cases? Let me just make that clear. So our first case is if lambda, so our real number, is is greater than 1. So if lambda is greater than 1, then our vector a bar would increase its magnitude. That means the length of this arrow would increase. So when lambda, or when our real number, which we're multiplying by a vector, is greater than 1, then the magnitude of the vector increases. In our second case, if lambda is smaller than 1, is smaller than 1 but greater than 0, this is our second case. So if lambda is smaller than 1 but greater than 0, the magnitude of the vector decreases somewhat in this way. So let me just make this. Yeah. This means that the magnitude of the vector decreases. So if you can tell from this figure, one second. Yeah. If you can tell from these two, this case 1 and case 2, these two lines are parallel to each other. So we can say 1 and 2 are parallel. Now let's go on to our third case. A third case is when lambda is greater than -1, but it is let me make this. Lambda is greater than -1 but is smaller, oh wait, my bad, is than -1 but is smaller than 0. What would happen when lambda is greater than -1 but smaller than 0? This would mean that the magnitude would decrease and the direction changes. So if you can, let me just make this a bit, yeah. If you can tell, these both are anti-parallel. So their directions are different, but they're still parallel to each other. And let me write the fourth case down here. In a fourth case, when lambda is smaller than -1, the magnitude would increase but in a negative direction, as what happened in the third case. But in the third case, it was like this. So you can see these both are again parallel to each other. So this would be anti-parallel to the first and second, and so would this. And these both are parallel to each other. So the third and fourth case are parallel to each other. Also important to know for later. So let me just make this kind of a clear diagram. First, second, third, and fourth. First case was if 1 second, lambda was greater than 1. This would mean that the magnitude increases. Second case was if lambda was greater than 0 but smaller than 1. Sorry. Second case, oh, it was this only. Is if it was, yeah, greater than 0 but smaller than 1, then our magnitude decreases but they still remain parallel to each other. Our third case was when lambda was smaller than 0 but greater than -1. In this case, the direction changes, the magnitude decreases and the direction changes. And our last case was when lambda was smaller than -1. This means that, oh wait, wrong diagram. A bar and the direction changes, that's it. So these are all different cases of different lambda values. These are our 4 cases of lambda multiplied by, so a real number times a vector. So these are all different cases of how the real number is different. Alright, and we're coming towards our last topic, which is collinear vectors, a pretty small topic. So any two vectors, say a bar and b bar, are said to be collinear when the if one vector, say a bar, can be expressed as a scalar multiple of the other, kind of like this, if this is a scalar. So I'll give a practical example of this so it'll be easier. So we all know that momentum equals to mass into velocity. We also know that momentum is a vector, mass is a scalar, and velocity is a vector. So p bar equals to m times v bar. So in this case, p and v bar are collinear. So if a bar equals to lambda times b bar, where lambda is a scalar, then a bar and b bar are collinear. And that's it.